Hey everyone, welcome back. Today, we are diving into a really fascinating discovery in the world of AI search, and it's one that kind of flips the script on one of its most important algorithms. It's a great story about how sometimes the most complicated solution, well, it isn't the best one.
So let's just kick things off with a pretty wild question. What if a core, fundamental feature of an algorithm that's used by huge systems like Pinterest and Spotify was actually providing zero benefit? I know, it sounds kind of impossible, but that's exactly what we're going to unpack today.
All right, so let's get right into it. This is all about some recent research that seriously questions a basic assumption about how we find similar items. Similar ideas, similar images inside the gigantic datasets that really power all of modern AI.
First up, let's set the scene, because it's important. The big challenge for modern search isn't just about finding exact keywords anymore. It's about finding an idea, right? Like, when you search for an image of a happy dog, you don't just want photos that are tagged with the words happy and dog. You want pictures that actually capture the vibe, the whole concept of a happy dog.
Now, the tech that makes all this possible is called vector embeddings. The easiest way to think of them is like numerical fingerprints for anything. An AI model takes a piece of text, or an image, or even a sound clip, and it turns it into a long list of numbers. That's the vector. And the real magic is that similar concepts get similar fingerprints. So the vector for king ends up being really close to the vector for queen in this big mathematical space. But, and this is a huge but, there's the problem of scale. Modern vector databases can hold billions, literally billions, of these fingerprints. So if you had to compare your search query to every single one of them, one by one, it would be painfully slow. It's like trying to find a specific sentence by reading every single book in a massive library. It's just not going to work for apps that need answers right now.
So to solve this problem, the industry pretty much rallied around this brilliant algorithm called HNSW. That stands for Hierarchical Navigable Small World. And for years, it has been the undisputed king of fast vector search. It is the industry standard, and for very good reason.
So how does it work? Well, imagine you're trying to find an address in a huge city. HNSW basically builds this man-made transportation network. The very top layer is like a sparse expressway with these really long-distance connections that can get you into the right neighborhood super fast. Then, as you get closer, you drop down to the lower, denser layers. Think of these as the city streets and the local roads that help you find the exact house you're looking for.
The search process itself is actually really elegant. You hop on at the top-level expressway, you cruise along these long-range connections to get into the right general area, and then you descend down to a more detailed layer. And you just repeat that process until you're on the very bottom layer, the local streets, where all the data points live, and you can easily find your destination.
And this is exactly why HNSW got so popular. It's incredibly fast, it's super accurate, and you can even add new data on the fly, which is awesome. It seems perfect. But it has one pretty significant drawback. Building and storing all those layers, all those expressways and city streets, takes up a ton of memory.
Now, this memory cost was always just seen as a necessary trade-off, right? The price you had to pay for all that speed. But that leads us to the big central question here. For the kind of really complex, high-dimensional data we use today, we're talking vectors with hundreds, even thousands of dimensions, is this carefully engineered, memory-hungry hierarchy actually doing anything useful?
To find out, a group of researchers decided to put this exact question to the test. And in their paper, which has my favorite title, Down with the Hierarchy, they ran a bunch of tests on massive datasets to see what would happen if you just got rid of the hierarchy altogether.
And the results they found were, well, they were absolutely stunning. They compared the full multi-layered HNSW against a version that only used the bottom layer, just the local roads, no expressways. And what they found was that on this modern, high-dimensional data, the performance was identical. The complex hierarchy gave them no discernible benefit, not for speed, not for accuracy. It was all cost and absolutely no gain.
I mean, that is a wild result. It's like discovering that a city's multi-billion-dollar highway system is completely useless. So the next logical question is, why? If the highway we built isn't helping, how are searches still so fast? Well, the paper proposes this beautiful explanation. There was already a natural highway there the whole time.
The answer lies in this really weird phenomenon of high-dimensional spaces called hubness. It turns out that in these complex mathematical spaces, a small number of data points just naturally become hubs. They're super popular. They show up as a close neighbor to a huge number of other points. You can think of them like these major crossroads or intersections that connect totally different parts of the city, and they form all on their own.
So this just completely reframes our entire understanding. The old theory behind HNSW was that we had to build an artificial expressway system to get that fast, long-distance travel. But the new reality, what the researchers are calling the hub-highway hypothesis, is that in high-dimensional data, a super-efficient highway of these well-connected hubs just forms all by itself, naturally.
And the paper puts it perfectly. They found that search queries just naturally find their way to these hub nodes really early in the search. They kind of hop from hub to hub, traveling along this natural highway system. And it works so well because these hubs are incredibly well connected to everything else. The man-made hierarchy was redundant because nature had already provided a better one, for free.
So what does this all mean in practice? What's the takeaway? Well, it points towards a future for vector search that's much simpler, way more efficient, and yeah, a whole lot flatter. Let's talk real numbers. By simply not building those unnecessary hierarchical layers, the ones that were doing nothing anyway, the researchers found they could save about 38% of the peak memory that's used when you build the index. And that is a massive efficiency gain for any large-scale system. It frees up resources and it cuts down costs.
So this changes a lot. It means vector databases can be designed to be way simpler and much less memory hungry. We get the exact same top-tier speed and accuracy, but with way less overhead. As the paper kind of cheekily suggests, for high dimensions, maybe the H in HSNW should just stand for hubs. It's just a brilliant reminder that sometimes our most complex engineered solutions are just recreating something elegant that nature already figured out for us.
And that really leaves us with a final thought, doesn't it? This discovery wasn't about inventing some new, more complicated algorithm. It was about questioning an old assumption and discovering a simpler, hidden truth that was there all along. It really makes you wonder, what other complex systems are we building today that are just covering up a simpler, more elegant, natural solution?